Astronomers have found evidence of a rare missing link black hole in our cosmic neighborhood. It is an intermediate black hole located around 6,000 light-years away in the Messier 4 star cluster. So far, we've only observed two distinct black hole classes: the gargantuan supermassive black holes, lurking in the centers of galaxies and weighing millions to billions of times the mass of our Sun, and their smaller counterparts, the stellar mass black holes, born from the violent deaths of massive stars and weighing just a few times the Sun's mass. However, a groundbreaking discovery in a nearby star cluster is challenging this dual classification and offering a tantalizing glimpse into a previously elusive category of black holes. Astronomers have unveiled evidence of a rare intermediate mass black hole, filling the mass gap between the supermassive and stellar black holes. But what makes an intermediate mass black hole, or an IMBH, so special? Why is it so difficult to find a black hole of this category? Finally, and most importantly, how did astronomers make this exciting discovery? Based on existing research, one of the prime locations to look for intermediate mass black holes is within the core of globular clusters. A globular cluster refers to a tightly bound system of thousands to millions of stars, held together by gravitational forces, all originating from the same molecular cloud. These clusters are commonly situated on the outskirts of galaxies, revolving around the galactic center. To date, some potential intermediate mass black holes have been pinpointed within such clusters, encircling our very own Milky Way galaxy. For example, in 2008, data from the Hubble Space Telescope led astronomers to postulate the existence of an IMBH in the globular cluster Omega Centauri. Subsequently, the Space Telescope identified two more credible candidates for these intermediate mass cosmic entities in 2009 and 2020, located within the densely populated star clusters on the outskirts of other galaxies. Furthermore, NASA's Chandra X-ray Observatory has also played a crucial role in identifying potential hosts for intermediate black holes, particularly in the year 2018. Many of these candidates have been suggested to possess masses ranging from tens to thousands of times that of our Sun. But the problem is that these candidate objects are situated at considerable distances, and the available data has been insufficient to firmly confirm these hypotheses, leaving most of these findings inconclusive. This is precisely why the recent investigation into M4 holds significant importance. Nestled approximately 6,000 light-years from Earth within the constellation of Scorpius, Messier 4 stands as the nearest globular cluster to our planet. It has an estimated age of 12.2 billion years and measures 75 light-years across. And here's how astronomers figured out that there's an intermediate black hole hidden in the dense cluster of stars. In the new study, scientists analyzed 12 years of data from the Hubble Space Telescope and combined it with information from the Gaia mission. This collaboration aimed to closely examine the stars at the core of this cluster. By doing so, the researchers tracked the precise movements of 6,000 stars within this cluster. When astronomers closely studied the orbits and velocities of these stars, they found something strange. The stars were being influenced by a dense mass of nearly 800 solar masses situated at the cluster's center. Now, this discovery raises a critical question. How is the mass distributed? Could it be a singular entity like an intermediate mass black hole? Or is it a collection of smaller yet massive objects, such as individual stellar black holes that haven't merged? Despite M4 being the nearest globular cluster, it's still impossible to resolve the individual stars at its densely packed core. But there's a clever way to solve this problem. Even though we cannot directly observe what's happening at the center of the cluster, Estimating the distribution of the central mass in such clusters is possible by studying the motion of high-velocity stars. In simpler terms, if a high-velocity star is linked to a potential IMBH, its rapid speed can be attributed to a dynamic kick following a close encounter with the compact object. Moreover, certain models have indicated that if an IMBH exists at the heart of M4, there's a 33% probability of encountering a high-velocity star within the central region of the cluster. Remarkably, researchers managed to identify a high-velocity star in their observations of M4. In this figure from the research paper, the green star represents this high-velocity star. Yet the presence of a high-velocity star only signals the presence of concentrated mass at the core of the cluster. It doesn't conclusively define its nature. Following this, the researchers conducted simulations to see the impact of removing the high-velocity star on the nature of the central mass. The findings revealed that the cluster exhibited the same mass excess at its core, even after removing the high-velocity star, although with a slightly more extended distribution. This extended distribution could potentially suggest that the central mass comprises a collection of individual objects rather than a solitary IMBH. However, in the case of M4, mass is not spread across a large enough region of space to be a swarm of dense objects. Furthermore, even if the detected mass originates from multiple objects, the system would be unstable. The reason is that the mass found at the core of M4 is equivalent to roughly 40 smaller black holes. Considering the observed movement of the surrounding stars, the only plausible explanation emerges if all these individual black holes were compressed within a region merely 1/10 of a light-year in diameter. Clearly, imagining the peaceful coexistence of 40 black holes in such a small space poses a challenge. Mergers and ejections would likely be inevitable. Also, a swarm of black holes would be so close together that they'd essentially create a mess. The gravitational interactions would send stars flying out of the cluster, smearing it chaotically across the sky. Astronomers have already seen the effects of this in a cluster of stars named Palomar 5. So this is how astronomers have concluded that whatever mass is lying at the heart of the star cluster is not from multiple smaller black holes, but from an intermediate one that's about 800 times the mass of the Sun. This makes the newly detected black hole of M4 an intermediate mass black hole. Astronomers now aim to gather more data from the future observations of M4 by Hubble, Gaia, and the James Webb Space Telescope. Currently, the mechanism behind the creation of stellar mass black holes is well understood, typically involving the core collapse of massive stars or their merging. However, the origin of supermassive black holes remains remarkably enigmatic. The precise process by which they grow, whether via successive mergers with smaller black holes or through the accumulation of matter, remains undetermined. In this context, the investigation and analysis of intermediate mass black holes stand to provide a valuable perspective into this unresolved mystery. Recently, the James Webb Space Telescope found signs of supermassive stars at the edge of time. They are unlike anything we've seen in the universe so far. If you missed this episode, be sure to catch up on this exciting discovery.